Right then guys, I think we're going to make a start. Thanks everyone for coming. My name is James and I'm going to be doing a talk today about AppCL LSM, and I'm going to tell you what that is in a minute. This doesn't work. I forgot that. That's just a pointer. It doesn't actually change anything. So, first thing is about me. Like I said, my name is James Johnson. I'm a student at Leeds Beckett University. I'm in my final year studying computer forensics and security. AppCL LSM is being developed as part of my final year project this year. Also heavily involved with Leeds Hacking Society, that have also been able to attend to this conference. There's quite a lot of them in here. And just off the back of that as well, if I'm not doing uni work or anything like that, I'm on my motorbike. That's all there is to me, pretty much. So what am I going to be talking about? Well, the talk's split into three sections. The first section is titled ACLs and PACLs. Okay, and I'm going to go into that in a bit more detail in a little while. Second one is called the Linux Security Module Framework, and the last bit is about my module itself, AppCL LSM. So just in a shortened way, what I'm actually going to be talking about is access controls, a load of acronyms, MAC, RBAC, DAC, ACLs and PACLs. We'll be going over all of them. You'll know what all of them mean by the end of this. We're going to talk about the difference between user-oriented and application-oriented access controls. We're going to talk a little bit about the Linux kernel, some kernel data structures, the Linux Security Module Framework, and then how AppCL LSM uses the Linux Security Module Framework to implement application-oriented access controls. That doesn't work again. I'm just going to put that down. So, first section, we've got ACLs and PACLs. We're going to start off with access control. What is access control? Well, a definition of access controls is that it's a set of controls to restrict access to certain resources. This is something that we all have, access controls. We've got this in place throughout our lives. Our front door, we don't let just anyone walk into our house, you would think. Then we've got at work, in the gym maybe, we've got access controls in place there. On your phone, might not be a thumbprint, might be a passcode, you've still got access controls in place there. Your social networking. Even a roller coaster. You have to be a certain height to get on that roller coaster, and you have to queue in a certain line to get on there. There's access controls before you're allowed to get on that roller coaster. So the access controls I'm going to be talking about is related to computers, specifically Linux permissions and Linux access controls. So now I'm going to go over all the acronyms I muttered over quickly earlier. We're going to talk about DAC, which is discretionary access control. As part of that, I'm going to talk about access control lists and the idea of a program-based access control list. Then I'm also going to mention, although it's not the topic of this talk, what mandatory access control is and what role-based access control is as well. So we'll start, what is an ACL? Well, an ACL is an access control list. Again, like I said, we're talking about specifically here Linux permissions and Linux access controls. So an access control list tells a computer the access rights and permissions that a user has to a particular system object. We'll just break that down a bit. So the permissions are what the user is allowed to do. Specifically in access control lists, we're looking mainly at read, write and execute permissions. An object, directory, file, something like that. So when we're looking at it, our access control list tells a computer what that user is able to do to that file. If we look at it graphically here, we've got a file over here, directory, symlink, hardlink, anything like that. And it can have an ACL attached to it with the user and the read, write, execute permissions on there. This is what we call user-oriented access controls because it's defined by the user themselves. So what is a PACL? And the PACL idea is really what my final year project has been about. So in the same way, it tells a computer the access rights and permissions that a program or application has to a particular system object. So the only difference there is that we're specifying it by application rather than by user. And again, look at it graphically, we've got our file over here, and we've got our program-based ACL attached to it there. Again, this is just an overview, looking at it sort of theoretically like that, and we'll go into more practical details about how that works in a minute. So this has given us the idea of user-oriented access control and application-oriented access control. Like I said, I'm just going to talk about MAC and RBAC. So mandatory access control labels file system objects, so our files, directories, with a classification. It then assigns a user a classification or a clearance. The access is then granted based on checking the user's clearance against the object's classification. So if we have an example here, we've got an object that has a classification of secret, and we've got a user that has a clearance of secret. That user is able to access that file under Mac. If that user had clearance of guest and wasn't able to access objects with the classification of secret, they would then not be able to access that file. So the rules and criteria in Mac and mandatory access controls, they're defined by the system administrator. So normally you would find mandatory access controls in something like a government institution, a big organisation where the people at the top want to really lock down what their users are able to do. And the end users can't change that criteria there. So now going on to role-based access control. The difference here is the access is defined by the ability of a user to perform a task. So rather than labelling each object, we're looking at the tasks that a user is trying to do. Tasks might be viewing a file, creating a file, modifying a file. And like we had classifications and clearances before, here we've got our roles that are assigned to users. And that role determines what task that user is able to do. So again, in an example, we've got our object, our file, and our user with our manager here wants to modify that file. The task is to modify, the role is the manager, and in this situation, the role of manager is able to perform that task. Say it was somebody working in support, they don't have the same role, they would then not be able to perform that task and modify that file. So it's an alternative to object-by-object based access control, as I mentioned before. So rather than having to label every single object and carrying it out like that the whole way through, you can easily add, create, change or remove roles. And makes it quite a good system to roll out if you want to sort of be able to manage it like that. So we've now gone over DAC, ACLs, PACLs, MAC and RBAC, and hopefully now to all of you, they're not just a load of acronyms. A lot of you will have heard of a lot of it before anyway. So, implementation of access control mechanisms. Again in Linux. So access control lists are configured by a user, or by a group, or by users not in that group, also known as other. Now the way we do that in Linux is we use the package AppCL. And you can do that on a Debian system with sudo apt-get AppCL, and it gives you the tools set fAppCL and get fAppCL. I say AppCL quite a lot in this talk, by the way. So here we've got an example of a set fAppCL command. The first bit specifies the rules that you're wanting to set to this file. The rules can be defined by user with the U prefix at the start. You can define it by group with the G prefix, or you can have it on your other with your O. You then identify the user by its UID and the permissions for that. Groups are identified by their GID, permissions for that on the end there. So if we look in this example as we had before, the user rule here, because it's got the U, the user James is able to read and write that file, home some file. And looking at it graphically how we did before, that would look like this. This file has an APL attached to it. The user James can read and write but cannot execute. So here we go, they can read but they can't execute. The -X option allows you to remove the permissions that are set on that file. So what's the problem? Or what the problem? I think we're going to have what the problem on a couple of slides here. So under traditional access control lists, applications inherit the privileges of the user that runs them. So you have an application calculator, say root runs calculator, calculator then inherits the full permissions of root. Now the question is, does calculator need the same permissions as root? I guess it kind of depends what it's calculating, but generally a calculator doesn't really need, all the permissions of root. It's just an example anyway. If we think about a lot of applications, they don't actually need the full set of privileges and permissions that the user running them is granting them. So here we can set an APL for the user James to have no permissions on this file. So the user James would not be able to read it, write it or execute it. Now if the application went to read that file, it would be allowed to. And what it looks like here, I understand that root has more permissions than the user that was running it anyway. So if root was to run it, it would have the full permissions, but it's just to just to show you how an application inherits all of those permissions and then can access files that it might not necessarily need to, or the user doesn't want it to. So this is pretty much what I've said here, where they don't need the same permissions, so applications can then misbehave, either by accident or through malicious intent. And it can leave system resources vulnerable, just to applications abusing their privileges. That's the whole idea behind this program-based access control list that I'm going through today. So one aim of AppCL LSM, which is the module I've been developing, is to create the program-based access control list, a PACL, to prevent applications from inheriting the privileges of the user that runs them. That's the first and the main aim of what I'm doing. Another aim for the module comes down to the complexity for the user. So this is quite a fancy sentence, but an increase in granularity of the security policies leads to an increase in the complexity for the user. That basically means that as security policies get more and more complex, it gets more and more difficult for users to understand what they're implementing and be able to implement them effectively over a large area. So I'm now going to tell you a little story. You're going to have to imagine for a minute. Okay, and it's the idea of this effective security versus potential security. So probably right now, a lot of you want to be here. A lot of you probably want to be in Costa right now. And we've probably all seen this situation before. You know, someone parking in a place they probably shouldn't be, and blocking where you are. So I'm not claiming to be a Photoshop genius in any of these pictures that come up. So in this, we want to get to Costa, we're blocked in. Now we're going to look at this as from an effective security versus potential security standpoint. And on the side for potential security, you could have a government-issued, bulletproof, limousine, vehicle, car, whatever you want. You know, that's bulletproof, is going to get you there, really safe, you're going to be absolutely fine when you get there. So we've got potential security. On the other hand, for effective security, we're looking at something that's not quite as big, something that's not quite as complex, not quite as secure, and, well, I found this, and I thought, not quite as secure, but that works. So you still want to get to Costa. Now this is the problem with potential security. I couldn't fit him on the drive, never mind get him off. So you didn't get to Costa. On the other hand, fits on there, I think he could probably fit between the wheelie bins over here. So you get to Costa. And really, the lesson from this story is what use is a bulletproof car to get to Costa if you can't get it off the driveway? And that's really what I want you to take from that story. So it's the idea that the level of security a user is able to implement versus the potential security benefit offered by that service or control. So another aim of AppCL LSM is to provide this human readable abstraction of the policy so that users are able to understand what they're implementing, they're able to configure them, and they know exactly what they are putting in place on their systems. So there really I'm aiming for a high level of effective security, like it says there, that through controls that users are able to understand and manage. So the next part of my talk, I'm going to be talking about the Linux Security Module Framework and how it allows the development of additional kernel level security. The focus is on access control modules with the Linux Security Module Framework. SELinux, which you might have seen on a number plate a minute ago, that is a mandatory access control solution that is built using the Linux Security Module Framework. There's also other ones such as AppArmor, SMAC, and there's a couple of other ones as well. So the talk before this, for those of you who are in here, someone spoke a little bit about the kernel. I'm going to look at it from a slightly different point of view. So when we look here, we've got our computer, and we've got lots of different things that make up our computer. What we're going to do is we're going to split this computer up into 4 different levels. We've got on the bottom our hardware, CPU, memory, hard drive, all those things that computers need. Then above that we've got our kernel, and then above that we've got the operating system and then the applications installed on there. Top 2 levels are our user space, the kernel is our kernel space, the hardware is our hardware space. The kernel's job is to communicate to the hardware on behalf of user space. Backwards and forwards, it handles that communication. And as was mentioned in the last talk in here, if you weren't in here, no problem, but user space communicates the kernel through system calls. And that's so that user space cannot directly access the kernel memory itself, and it has to do it through the API and through the system calls. So this is just an example of actually putting things in there again under Linux. You might have LibreOffice, you might have a GNOME desktop environment, and this is actually the development machine that I'm testing my module on. So hardware, it's just the same hardware as any other computer. It's running Linux kernel 4.3 with the AppCL security module enabled. It's got Debian 8.1.0 with the Debian desktop environment, and applications-wise, I'm actually using Nano as a test application, which some people have already turned their nose at, but the reason for that is I've actually been able just to completely shut Nano off the system. So it's, you know, if you want a module that can stop Nano doing anything on your system, I can give you that. I can give you that. So where we're looking at now with this Linux security module framework is in the kernel where my module is. I'm quickly going to mention some kernel data structures just because they're relevant to what I'm going to be saying as I go forward. We've got our inode, which is what most of us see as a file. And it's the file that's actually stored on the disk. So the inode is the attribute about a file that Linux stores. A file data structure, kernel data structure, is actually an open file object. So it's an inode on the disk, and when you go and open that file, there's then a file object for that inode as well. We've then got a superblock data structure that holds metadata for the file system. I'll be honest, the superblock, there's a lot of stuff held in there. So, what is the Linux Security Module Framework? Well, it provides a general kernel framework to support security modules. Like I said before, primarily focused on access control modules. By itself, it doesn't actually give any more security to Linux or the system that you're running it on itself. If you were just to compile it just as it is and run, nothing would be any more secure on your system. And actually, I've just put a little link down there. If you want to have a read a bit more about the framework itself, the NSA's website has actually got quite a good paper on it, but it's up to you if you want to go and visit. So how does it work? Well, the idea of it is that it adds security fields to these data structures that I was talking to you about before. Not just those data structures, but other data structures as well. It then inserts hook functions at critical points in the kernel code to manage those security fields, and then based off those security fields, you can perform access control. So here we've got a file. This has stopped again. There we go. We've got a file as we know it. In our kernel data structure, we've got our inode. We've got an application, because with our application-oriented access controls, we're going to have to be thinking about applications as well. And when an application is running, it's represented as a process. So the LSM adds security labels to these data structures. You then have hook functions to access and populate and make decisions based off those security labels and what you've stored in there. So with the inode object, we've got security hooks such as the inode alloc security hook, the inode free security hook, and they're responsible for allocating and freeing the memory that you need if you're actually going to put anything in the inode security label. Same with the file, there's an alloc security, a free security, and the same with the superblock as well. So we've looked at this, and that should all be making sense by now. So this is a diagram from the internet that explains how the LSM works, and this is where the hook functions actually come in. When a user runs a process, all of the standard Linux stuff, we'll call it Linux stuff, all of the standard Linux stuff happens until just before the access decision is made, and then the hook is accessed. So that means that all your standard DAC checks, so your APCL permissions that we've already looked at, any other security in Linux itself or that you've got going on, it will check all of that first, and then the Linux security module has the last say in whether access is granted. So I'm now going to go on to my module, AppCL LSM. And I'm going to talk about how AppCL uses this Linux security module framework to implement our program-based access control. So the first question here is, how do you define an application or a program? as we saw earlier, users are identified by their UID. If they're in a group, by their GID. So, like I said there, they're defined by their UID. Now, AppCL LSM uses the path of an application as the application identifier. One of the reasons for this is the aim for a high level of effective security for users to be able to understand what they're doing. If you get a user to specify an application by the path, people will be able to understand that, they'll be able to see and know what's going on. So an example there with our application nano, we've got the path bin nano for that. So the key development goals, I'm going to go through these one at a time. The first one is to label a process with that path of the application so that the process stores the path of the application, and we're then able to identify those applications based on the path. So as we saw before, we've got security labels on our kernel data structures, and AppCL wants to add the application path to the security label. The second bit is to label an inode with the PACL entries, our program-based access control list entries. So the application path and the relevant permissions need to be stored in there. So as we can see, as well as the application path being stored, AppCL wants to store the path and the permissions for that inode, so that it knows what permissions that inode has. It's then able to check the path to identify whether it's the current application. We'll come into that in a bit more detail. So as an example, with an actual application in there, we've got bin nano and R. So just before, as we saw this earlier, I'm just going to bring this back up, because as I go in and explain some of the hook functions themselves, it's worth bearing this in mind just to see where it's actually occurring when it goes on. So how we saw that set before, visually, it would look like this, where our application goes to access the file. It has read permissions so it can read it. It hasn't got write permissions, so it can't write it. And the last one is to store a representation of the permission entries in the file system extended attributes. There is a reason for this, and I think I actually cover it in a little while, so I'll see if I do, and if I don't, remind me and I'll come back to it. So again, to keep it on the level where users are able to understand, the extended attributes are going to be used to actually set the permissions to these files. And it's done in a very similar way to how ACLs work. So again, on Debian, you can do the sudo apt-get atch, which gives you the file system attribute package, basically. So rather than specifying your access controls, you're specifying a file system extended attribute. So the way that works, as you saw on the side here, we've got our setF attribute and our getF attribute. Now the set works in the same way as it did for the ACL, but we've got a couple of extra fields. Now the first one, the -n, is for the X attribute name, and that tells the security module which security namespace that this attribute is for. The -v is the value, which is going to specify the rules and also the path that we want to enforce, and the -h specifies the file that we're wanting to enforce the permissions on. So the X attribute namespace, as I've said, the -n specifies this namespace, but in the kernel, the security dot prefix in that name tells the security module that that extended attribute is for a security module. The AppCL suffix on the end of there tells my module that that security attribute is for AppCL. And so from here with the value, we can see that the application nano has read permissions on the file home/some file. Then the idea from this is after setting the extended attribute, it populates the inode security label, as we were talking about a minute ago, with the entries and permissions based on that value. So here we can see we set the value bin nano R, and AppCL will then populate the inode security label based on that. To see it visually, we've got our file, and we've then got our program-based ACL that we were talking about before, attached to that file with only read permissions. So it goes to read it, absolutely fine. Wants to write it, not allowed. So the way this works is you set your extended attribute, which populates the Inode security label, and that gives you your PACL. Over the next bit of the talk, sort of between now and the end, I'm going to talk about how AppCL actually uses the framework and the hooks itself that I'm using. So this will make a bit more sense. So the module itself is in a folder called AppCL, because that's the name of it. And in there, it's compiled into the Linux kernel 4.3. In the security subdirectory, you add the AppCL folder, and you have to edit the makefile in kconfig just for the configuration of the kernel when you compile it. The files in there, I've got AppCL LSM.c and audit.c, which are my main files in there, and then I've got the header files for those in an include folder as well. Again, there's a makefile and a kconfig in there for the kernel configuration and for compiling as well. So, AppCL LSM.c, it initializes the module, it's where the LSM hook functions are, and it's where the permissions are enforced. So this is where in AppCL LSM.h, the header file, our security labels are defined, and the actual PACL entries themselves, the data structure that holds the PACL, is defined in there as well. Then in audit.c, it just contains, at the moment, a few audit functions, which help the module check the path of the current process against the label on your Inode. It counts the number of permission entries that you've got, and it also does permission checks on that as well. And audit.h actually defines the security data structure that the path for the application is stored in, called task audit data. It sounds like a fancy name. So, last section in this talk then. Starting off in AppCL, we're going to look at the security labeling to start with. Now, the security labeling hooks that are relevant for this, we spoke about quickly earlier. We've got the Inode alloc security and the Inode free security. Like we said, there's also file, alloc, and file free. I'm not going to look at those today though. Now, this is a description of the actual hooks themselves that AppCL is using. This is the name of the security hook, AppCL hook name there, and this is what the hook does. So the alloc security hook allocates and attaches the security structure, as we mentioned earlier. And freeing it, then frees it. So we see here, it's at that last point, just before the action is made, that it's consulted and then you can follow out your actions. So if we look at the hook itself, and this is how I'm going to go through a few hooks. This first one is just to show you how I'm going through hooks so it makes sense, really. So with the Inode alloc security hook, it's got the Inode and the Inode security label. The alloc hook function sets an Inode security label to null and then applies it to that Inode. The free security hook, AppCL, sets the Inode security label to null and then frees the label that was stored on that Inode. So carrying on with the security labeling, this is now looking at labeling the process path. So it's stored in the credentials data structure, and so we've got four different hooks there for that. We've got our cred alloc blank, cred free, cred prepare, and cred transfer. It's basically the same as your alloc security and your free security, except when it comes to credentials like this, you've got to deal with transferring them over and also preparing a set before you actually populate it. I'm not going to go into each of them though. This is just a table, again, same table, but it tells you what each of those hooks do. The hook I am going to have a look through now quickly on this one is the BPRM setCreds hook, which saves security information in the security field based on information about the BPRM, and I'm going to tell you what that is. So the BPRM setCreds hook, so like I've said, it saves security information in the cred security field, and the Linux bin PRM structure, which is passed to this hook, is a structure used to hold the arguments that you use when loading binaries. So when a binary is loaded, it captures the path of that binary, and it stores it in the credentials for that process. So here, as we can see, AppCL, the BPRM hook, identifies the path for that binary and then stores it in our task audit data on our credentials over there. We then have, from that, our null Inode security label set and our process security label set. So going on to the extended attributes, we've got a set extended attribute, a post set extended attribute, a get extended attribute, a list extended attribute, and a remove extended attribute. Pretty self-explanatory what all of those mean, really. What these do is the setX attribute, it checks permissions for that user to set an extended attribute. So just before an attribute is set, all of your normal access controls go through, consults AppCL LSM, and it checks that that user has permission to set extended attribute. Now, at the moment, AppCL just checks that the user is running as root. And so the user has to run as root to be able to set the attributes. So, again, a table saying what each of them does, but pretty self-explanatory from the name, really. It checks permission before that. The only thing is the post set extended attribute. Like we said, set XApp checks your permissions to set them, and you post set XApp, you then deal with the attribute that you've set. So you have to do that in a separate hook itself after you've checked those permissions. So the entries themselves, and we were looking at this earlier, which gave us our PACL idea over here. So what actually is this? Well, the Inode security label stores an array of entries, and these entries store a PACL entry. That PACL entry has a tag, a permission, and a path name. And that's basically what this is. So on our security label, we've got an array of entries, which is our PACL entries over here. So, like I said about the post set extended attribute, after you've checked permissions to set your extended attribute, you can then update the Inode security field from there. So here, the first thing it does is it takes the name and it checks that it has the AppCL security namespace. Then it takes the value and it splits it into the path and the permissions based on the value that's been set. The function make AppCL entry then converts this into the AppCL PACL entry structure, and that's then stored as an entry on the Inode security label. Now this is just an example. This is some kernel log output. So here, can you see that on the white? So you can just see there I've set 3 values, all for nano, read, write, execute, and the the make PACL entry function has then split it up. So we've got the path and the permission, path, permission, path, permission. And that would then be stored as 3 separate entries on that array in the label. So now this should make sense, and you know what's happening between each bit here and what the PACL actually is. So now we've actually extended that idea to this, that we set our value, the AppCL LSM security hook then populates the Inode security label from that value, with our PACL actually being an array of entries on that label. Now that things are labelled, we've actually got to enforce the permissions, so our read, write, execute permissions. This bit isn't finished yet. The module is still under development, so there are still things that need to be done, but it's getting there. And we look really at two different types of permission hooks, really. And we've got our general permission hooks, and then we've got our more specific permission hooks. So as I mentioned earlier, audit.c has some important audit functions. For the rest of this, I'm only really going to talk about 3 of them. The check current cred path, which just checks that one of the PACL entries has a path name that matches the current process. Then it's got AppCL check permission mask match, which checks the permission mask against the PACL entries, and then check rperm match checks for a specific requested permission rather than a mask that's being passed to it. So, here we've got our Inode permission and our file permission. So the Inode permission is called in the existing Linux permission checks. So the Inode permission hook gives AppCL a hook in to also perform additional access control when Linux checks its permissions. So the AppCL check permission mask match is the function that's used in this hook. You pass the Inode security label, the current credentials, and the permission mask. So we've got the Inode permission hook, takes the Inode, checks the path against the path on the entries in the array, and then runs this function to check that the mask that's passed to it, its requested permission that the kernel is asking for, is present on the label. If it's not, if it's asking for write and it's only got read permission, then it won't grant access based on that. Then on more specific permissions, we're looking at an actual operation itself. So an Inode, the Inode create hook is called, funnily enough, every time you go to create an Inode. And the Inode rename hook, funnily enough, is called every time you want to rename an Inode. So the check RPER match, it takes the Inode security label, the current credentials, the requested permission, and because it's based off the other function, at the moment it also takes a mask, but those two, you pass the same permission to them, and it then checks that you've got the permission you're asking for. See that in action in the Inode create hook. Just before an Inode is created, AppCL is consulted. Again, checks the current credential path against that on the Inode security label. And then for Inode create, I've specified that you have to have write permission to be able to create that file. So if our entries had write permission on there, then it'd be fine. If it didn't, if it just had read and it was asking for write, then it wouldn't grant access based on that. So the next steps. The next steps, the literal next steps for me, is the problem with all of this is the Inode security label is stored in RAM. And so you set the Inode security label based off the extended attribute. This is what I was going to come back to, and I am coming back to it, so I did remember. You don't need to remind me now. The extended attribute, the file system extended attribute, is stored on the disk, whereas the Inode security label isn't. This is one reason that I've been using the extended attributes, so that when you reboot the system, there is still a record of the permissions that you want to enforce. So next thing that the module will do is it's going to repopulate the Inode security label in the same way it did on the post-setexapp hook, except it will do it when it reboots based on the value that's stored for it. So again, we can see here the same. I'm not sure why that's in there twice actually. But on the next steps there, the way this is going to be done is we've got some more hooks. There's quite a lot of hooks in the LSM framework now. When it first started, there wasn't as many, but there's quite a few now. Now the set security, get security, list security, notify security context, and set security context. There's a couple more. Basically, all of these have to be working together just right, and when you reboot, it will repopulate it. I haven't got it just right yet. So the set security hook, the idea is that it checks the security namespace again, and it then runs our make AppCL entry function to populate it based off the value that's there. So it actually works in exactly the same way, it's just calling it on a different hook. So rather than populating it when the extended attribute is set, it's populated based on that attribute when the system reboots. So last time back to this format, you're probably sick of seeing this image now. But we now have, from that, our application-oriented access control model. So then further development for this. After the next steps, and once I've got all of that working, two bits of further development I'm going to talk about quickly. The first one is application groups, and the second one is default application types, such as a web application type, you might have a P2P type, word processing type, something like that. So the first one, where we're looking at groups, as with ACLs, we saw they were stored with UID, perms, for group G, GID, perms. Now, to make it nice and simple and keep it nice for the user to use so that it reflects the ACL a bit more, Then we can just turn this into adding a U before the path and permissions to set our user PACL. Wouldn't be user, sorry, that would be application, not user on that second one. So here where it says user, that would be application. So ignore that. But group would still be group, but it would be an application group. And so you could set application groups. And you could have the other. So it would still reflect that. The only difference would be it would be application, not user at the top there. And the second one, like I said, is default application types. In the AppCL PACL entry structure at the moment, I have an unused field which is the E tag. Now that will be used for default application types. So you might have, say, a Word document or a word processing application, and you know that word processing applications need a default set of permissions. And so you would then be able to specify per application type rather than the application itself. And then any applications that fall under that type would be enforced like that. There's a bit more with putting default permissions and things like that in there, but that's somewhere that it can go from here as well. So, in conclusion, come back to this slide. We talked about access controls, talked about MAC, RBAC, DAC, ACLs and PACLs, user-oriented, application-oriented access controls, talked about a load of Linux kernel data structures, the Linux security module framework, and then for AppCL we've talked about the hook functions, the audit functions, the PACL design and future work on it as well. Has anyone got any questions?
Did you look at any of the alternative approaches that already exist? Say, for example, OpenBSD's Pledge, Syscall, or, for example, Oz from the secure desktop people?
I've mainly, part of the project has been to use the Linux security module framework. So a lot of what I've been doing has been looking at the existing modules there, which, as I said before, is like SELinux, AppArmor, SMAC, things like that. And the idea was to use that framework to just try and implement this model. As far as the other ones go that you mentioned now, I haven't looked into a lot of them too much at the moment.
So on the diagram you had in the middle of the slide deck, where you had the sort of chain of checks, and then you said that your module has the kind of the final say.
Yeah.
How does that work then? I mean, I'm guessing that the steps higher up the chain, if they fail, then your module will never be called into question. I'm thinking, like, if you say Nano has read access to a file, but the user doesn't have read access,
yeah,
would your module override it and give them read access?
Like you say, at whichever stage it's then denied access, that is where it would be cut off. So it then wouldn't consult anything further down than that. So if it's already off by that under the DAC checks, or if there's, say, an error, it then wouldn't carry that through.
How long have you been working on this for?
I started it at the start of my final year, so it would have been about September. Started research for it sort of in the summer, because before this I hadn't done any C programming before. Hadn't really looked at the Linux kernel that much, so did a couple of months research like that, and then yeah, been developing it since about September. But I've changed my mind on what needs to be done so many times between now and then. But yeah.
Is there any reason you're using the 4.3 kernel? Is there like more features in the LSM, or is that just...
The reason I'm using the 4.3 kernel is when I started, the current version of the kernel was 4.1.6, and I was developing against that. The problem with going from kernel version to kernel version is nothing is guaranteed to be the same between each version. So in about January, just before January, I decided to update to 4.3. I think it was just before January, because that's what it was at the time. And the thing that they'd changed was how to initialize all of the hooks. The whole way the LSM framework was what had changed. And I met with my supervisor and I basically said, I'm not updating kernel versions again before the project's finished. Because if I'd have, say, gone to do that now, there's a lot more in there and that would have taken a lot of project time to change that. But following the completion of the project for uni, I can then continue work on it to update it to the latest version there.
Does that make maintaining like a kernel security module quite difficult then, if they're just sort of...
It makes a good case for if you're doing something like that, submitting the work up. Because if you submit some code to the kernel community and something gets accepted, some of the maintenance on that kind of gets done by the people that control certain areas, and some of that maintenance gets done for you. So it's kind of to encourage people to submit their code and get it involved with there so that some of that gets done for you. Otherwise, it can be difficult going from version to version, depending what's changed.
Cheers.
And just abuse this and go to the question. Okay. So, am I right in the assumption that every time you make some progress on the module, you recompile the whole kernel to actually test it?
That's correct.
So, do you have a development pipeline or some strategy and script set up to do all of that for you? How exactly does the development process look for you? And also, do you do any automated testing on it?
At the moment, I'll be honest, as far as testing goes, there was quite a long time with development that there was actually nothing being printed out anywhere. It was literally just trying to get things to be in the right place. I'm sorry, could you ask that last bit again? I've just forgotten what that was.
Automated testing?
Yeah, so I haven't really been able to do a lot of testing like that. I do have a script, because I develop it using the IDE Atom, and so I develop it in there, and then I sync it to my Git, and then I've got a script that updates it into the kernel directory, and then does the compile there as well. So I've got that bit automated as far as going from there through to compile. But the testing side of it, that's just after every compile. I'm trying to do one specific thing, so at the moment I test that, and then I carry on.
So a couple of suggestions. Firstly, in terms of the fact that the Linux syscall infrastructure changes on a regular basis, you should probably have a look at Kshell, which allows you to do semantic patching.
Okay.
The other thing, on the security testing side, it would probably be worth you using Dave Jones's Trinity syscall fuzzer, because that's pretty much the de facto standard for the Linux kernel.
Okay. Yeah, brilliant. Thank you. Yeah. Anyone else?
With regards to testing, like how do you approach like making sure the modular building is secure from the outside, not just like enforcing on the test, but like, how do you make sure that you can't have like a buffer overflow in your code? Are you checking that kind of thing, or is it just that you're going to build it first and then test that later?
At the moment, because everything that happens within the kernel is in kernel space, the problem that you've got is like with the setting extended attributes and things like that, you're obviously taking user input and you're then putting that through, and that's where your buffer overflows can come in and things like that. So there will be some checking in place for that, but at the moment there isn't. The extended attributes thing is something I've been doing quite recently, so we'll be putting some checks in place there, but at the moment that's not in there.
Okay, cool.
I'll distract. Are you planning on, I guess once you finish, obviously not before, but are you planning on open sourcing it at all? Or?
It is actually open source now, and I've got a development site for it as well, which just has like my development blog as I've been going along. Part of the reason I've done that is there's not a lot of material for people getting into kernel development and kernel programming. There's not a lot of material out there for people that don't necessarily have a lot of knowledge for it in the first place, and when I started I definitely didn't. So the development blog that I've done, I've definitely got out there just so people that maybe are interested in it can see the stuff that I stumbled upon, the stuff that I learned as I went along, and maybe just a bit of a resource for people wanting to get into that. But if any of you want to have a look at that website, see what the updates are, just go to AppCL LSM.org or .com if you want, up to you. And you'll be able to see the updates from there.
Kind of a long shot question, but do you know of any modules like this that exist for the OS X kernel?
I don't.
Sweet, no worries. Cheers.
Anyone else?
Bit of a long question, but may I ask how many user contributions you had in the GitHub repository so far?
No.
Sorry.
That's all right, but to be fair, I haven't really been publicising it or sending it out at the moment, especially with stuff where it was at the beginning stage. I've been using it more than anything just to maintain my versions and stuff like that. But yeah, no, none. So if any of you want to go to that website, there's a link to my Git on there. If any of you after today want to go and make some suggestions, that'd be great. Some feedback on it, anything like that, go have a look. Drop me a message or something with what you might be thinking about it, that'd be great.